All right, good afternoon, everybody. Thanks for coming out. I'm Paul. I am the manager of the observatory here at the Thunder Nature Center Observatory. And thank you for coming out. If you didn't know, we are a private nonprofit educational organization. And our mission is to educate the public. So we have programs like this. We have public programs like we had last night for viewing. And then we have educational programs during the day, both nature, living nature related, and then we have our astronomy at night. By coming to public programs, which we do year round, it helps actually kind of subsidize a lot of educational programs because we do school groups all over Central Oregon, Deschutes, Jefferson, Crook County programs. We've done Lake County. We even do some programs from schools over in the Willamette Valley, so Portland, Eugene. And on occasion, we've had a few groups come down from Seattle even. So by supporting us here, you can help with all of those kind of programs. I'm gonna turn this over to Tim Merrill, who is going to be our astronomy interpreter for the night, but he is actually our operations and facilities specialist out at the observatory, and he takes care of all the wonderful equipment we have out there. So we got him to do this program on the side when he's usually out there busy cleaning mirrors and fixing mounts and things like that. So thank you, Tim, for doing this, and I will turn it over to Tim.
Awesome.
How's everyone doing tonight? Good. Thanks for coming. Again, my name's Tim, and I'm an interpreter here at the observatory. I've been here for a little over 10 years now. And I still have just as much enthusiasm and love as I have since I started. So hopefully I can convey some of that to you guys tonight. So interpreter, some of you might wonder, isn't that someone who helps someone else understand a different language? Well, here, in our case, myself and my fellow interpreters, who work out at the observatory and over at the Nature Center, we're here to help you understand what you're going to be seeing. So I help you guys understand what you see through the telescopes. So any of you who are staying for the viewing afterwards, feel free to come up and ask us questions on, like what you're looking at. If you want to know a little bit more, you don't know what you're looking at all, and especially speak up if you look through the telescope and you don't see anything. Okay, so that we want everybody to see something through the telescopes. And typically, if you don't see anything, usually, there's either a cloud passing by or somebody has actually grabbed the telescope and bumped it off target. So that's something that you guys want to remember not to do, is to grab the telescopes, because they do get knocked off target really easily. All right. Oh, one question we get asked a lot out at the observatory is where's the bathrooms? There is no bathrooms over at the observatory, so if you do need to use the restroom, I believe this one will be open all night long. Just on the other side of the door, there's a bathroom right back here. So. All right. Well, just a little bit about the observatory. Like Paul was saying, we are a nonprofit organization, dedicated to educating the public about space. We started in the early 90s. The first thing that was built was our dome. Before that, people were just bringing telescopes down to the parking lots, and it really caught on and people loved it. So we got some donations, some grants, we built the dome. And then in 2000, the first roll-off roof was built. And we have 6 telescopes in there that were all donated to us with either directly or through funds. And then the back patio you can see at the top of the image here. We had some roll-off buildings there and more telescopes. That was built in 2014. And then the most recent expansion was in 2021 when we built the second roll-off. It's not actually in the image, it's on this side of the dome. And that was again through mostly donations, and grant money. At this point, I would say if we particularly move you tonight, and you guys really enjoy your time, You can jump online if you would like to help out our organization, or you can email our director Shannon. Or a really good way to support our organization is actually just by shopping at the Second Turn, which is a thrift store that's run by volunteers, and their proceeds come to the Nature Center and Observatory. The Second Turn is actually just on the south side of Sun River. You just have to go over the bridge, and it's kind of on the left out there. So that's a really good way to support the organization. All right, the talk that I'm going to be giving tonight is called Lunar Origins. And it's going to be about 45 minutes to an hour probably. I'm going to be talking about the most current scientific theory on or hypothesis about the formation of our moon. So I'm going to be covering, where the moon came from and kind of, why it looks the way it does. Okay. So this story, this hypothesis, has changed over the years, because as we grow and as our knowledge increases, so does the scientific hypothesis, and that's the way science works. If we always thought, science was stagnant, we wouldn't actually ever learn anything, right? So yeah, as we grow and as we understand more, this story has changed and it's improved, through the years. So let's just talk about a couple of those old hypotheses real quick. One that comes to mind is the capture theory, where, the Earth and the moon were out in space and the moon was passing by and it got a little too close to Earth, and Earth's gravity reached out and grabbed it and pulled it into its orbit, and then it just became our moon, ever since, and it lived with us. That's the capture theory. Well, once, our math got to a point where we could actually put this to the test, we figured out that it would be almost impossible for this to happen, just because the size of the moon and its speed and how far away it is, its orbit, just nearly impossible for this to happen, for the capture theory to be correct. Another one is called the fission theory, where we thought early that maybe that the Earth could have been spinning really fast. And so fast that it started to flatten out and kind of bulge out, and then eventually just kind of bloop, the moon just kind of blooped out the side. That was also, disproven by math. And essentially, once we were able to run through the formulas and figure out, if the Earth could actually, start spinning that fast, we wouldn't get a bloop. The Earth would essentially just kind of pop and disintegrate if it spun fast enough to, bloop or a moon outside. And then a third one that actually still has a little bit, following, still a little bit of merit is the co-accretion theory, where we think the moon and the Earth just kind of coalesced and formed in the same kind of nebulous cloud in our early solar system. They just formed at the same time. All right, so that one is close, but it doesn't answer a lot of questions. There's still a lot of things like the core difference in size of the Earth and the moon. So the moon is known to have a very small core density. So it has a very small core compared to its overall size. Whereas, it just doesn't match the other things in the solar system. And if the moon and the Earth formed at the same time, we would think that ratio would be proportional between, the two bodies. But they're not. So that is what, as well as, the co-accretion doesn't really explain like the orbit, of the moon. And I'll get more into that later. So the theory that I'm going to be talking about, was first proposed in the mid-70s. And then really started to take hold like in the 80s, in the mid-80s, following the lunar missions, where we actually went to the moon. We touched down and we went out and did experiments and we learned all sorts of new science. We actually brought back samples, and then our knowledge increased, our scientific hypothesis grew, and improved, because of this added knowledge. So who knows the official name of our moon? All right, this is actually a trick question. Anybody know the name of the moon? It's right, it's called the moon. Any moon is the name of our moon. All right, so I find that a little funny because, when we look out into the solar system, all the other moons have names, like Jupiter, the 4 largest moons are Io, Ganymede, Europa, and Callisto. Saturn, Titan, Enceladus, Dione and Mimas. Mimas, no,
Yeah.
Mimas?
Yep.
Okay. Yeah, the moon is just the moon. It's been, throughout other cultures, it's been known as Luna, it is a name for it. But the official name is the moon.
With a capital M.
Yeah, with a
Yeah.
capital M, yes. All right, how many moons do we have? This is not a trick question. Nice job. All right, we have 1 moon. All right, so I was talking about Jupiter and Saturn. Jupiter, when I first started giving this talk, I would say, Jupiter and Saturn have over 60 moons, but since then we've discovered more. Jupiter has almost 100 moons, and so does Saturn. Saturn has almost 150 moons. So I just find that incredible. And can you imagine if we had over 100 moons and we looked up into the night sky? It would just be nothing but moons, right? It would just, especially if they were all full at the same time, astronomy would be awful, right? We wouldn't see, it would be so bright. No, but we just have our 1 moon. How many moons does Venus and Mercury have? I'll give you a hint, it's less than us.
0.
0, that's right, 0 moons. All right, so at least we have our 1 moon. And we love, our one, especially out at the observatory, we love looking at it through telescopes. We love looking at it through binoculars. I love to just go out and, in the summertime, just lean back in a lawn chair, just gaze up, at the night sky, it's nice and warm. You hear the crickets, you hear maybe some frogs, the stars are out, and the moon is just passing across the sky, right? And it's just kind of always there. We just kind of honestly start to forget about it. We kind of take it for granted. The moon, it's sometimes it's full like this, sometimes it's crescent. Sometimes, it's up during the night, sometimes it's actually up during the day, like it'll be tomorrow morning. If you look over the mountains to the west, it'll be up during the day. But it's always there, and we kind of, again, just take it for granted. But I would like everyone to take home tonight, the moon is a whole nother world with all of its own history, and all of its own features, all right? So when we look at the moon with our naked eye, just gazing up at it, we don't see very much. We just see those light areas and those dark blotchy spots. And being humans, our imagination just starts to take over. Kind of like looking at the clouds or looking at, the constellations, and we start to see, like the man in the moon, right? We start to see a face on the moon. And something that I've actually heard a lot since I've worked here is a lot of people actually grew up with the rabbits in the moon, especially Asian cultures. They grew up, with the rabbit in the moon. But again, it's all just, our imagination. I like to go out and just imagine like the alien in the moon, right? Get all those dark spots there. You can make 3 eyes out of that, right? But yeah, we don't see very much. But when we point a telescope at it, we start to see a lot more detail. We start to see that these light, areas are full of craters, just covered in these craters. And the dark blotchy spots, they're actually a lot more smooth. And there's not as many craters on there, on the darker areas. And if we zoom in more, and keep zooming in. Now, this is farther than we can see with any telescope on Earth. This is actually taken with a satellite that's orbiting the moon right now. You guys know we have satellites orbiting the moon. We have, thousands and thousands of satellites now orbiting Earth. The moon deserves a couple of satellites, right? Well, this satellite is called the LRO. It's the Lunar Reconnaissance Orbiter. And it's taking these fantastic images. We can actually see, I don't think I have any of them in this slide, but you can actually see some evidence of stuff that we've left behind on the moon with the LRO. But with this image, you can see this crater right here. This crater is about 50 miles across. There's another crater here, and like this ridge, this is a mountain range in between the two craters. And then here, right in the middle of this crater, there's a mountain, and then there's crater inside of crater inside of crater, all over our moon. All right, well, why does the moon look the way it does? Why does it have these lighter areas and those darker areas? And for that matter, why do we even have the moon at all? Why is the moon there? Well, to answer those questions, we have to go back in time, back to the beginning of our solar system. So back then, when our sun, this is kind of blown out here, is a little overexposed, but the sun is right here in the middle. And a very young sun, and this giant swirling disk of debris is we call an accretion disk around our young sun. And it wasn't exclusive to just our sun. When we look out now, when we look out into space and we see new solar systems forming, we see them with these giant swirling accretion disks of gas and dust. So this gas and dust that's swirling around is like a nebulous, kind of stew that eventually starts to develop dense pockets. All right, so these dense pockets, they start to come together, and we get more gravity in these pockets. All right, and when you get more gravity, you have more mass, and then because you have more mass, you have more gravity, and it pulls in more stuff, and all of this gas and dust, it eventually, starts to develop into more solid stuff like rocks. All right, and then you get these rocks that are smashing into each other and then forming into bigger rocks. And we actually see evidence of this. We have a good picture of an object that was taken back in 2017 when we flew out to Pluto with the New Horizons project or probe. You can see this is actually two big rocks that actually formed into one object because of the process that I'm talking about, because of gravity. So this is actually, this was actually pretty exciting, finding that back in 2017. All right, so as this takes place, the rocks just keep getting bigger and bigger and bigger and smashing into each other. And eventually, if you just continue this process, this snowball effect, in space, it pulls in from all directions at the same time. A body with gravity pulls in from all at the same time, all directions. And eventually, because of that, you start to develop spheres, okay? And because if you just keep adding stuff from all directions, it just starts to kind of smooth over. So these early spheres that started to form in our solar system, we refer to them as protoplanets, kind of like the first planets that started to form in this accretion disk swirling around the sun. Another name for the accretion disk is a protoplanetary disk. So we think that there actually, could have been hundreds, of planets forming, in this swirling nebulosity. All right. Well, if there was hundreds of these early planets, where did they all go? Well, we think, a lot of them could have been absorbed by the sun. A lot of them could have just smashed together and actually formed like the asteroid belt between Mars and Jupiter, or the other asteroid belt that's on the edge of our solar system out past the gas giants, out where Pluto lives. It's called the Kuiper belt. We think, that asteroid belt, could have been things just smashing together. They could have been hurled out of the solar system altogether because of the early chaos, but a lot of them actually became, the planets that we have today. All right, so Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune. And probably everybody is thinking, where's Pluto? Well, at least that's what everyone used to think. I think people are starting to accept that Pluto is no longer like an official planet. But I'll get to that in a minute. But yeah, by the way, anybody who stays tonight, we are going to be looking at Mars and Jupiter through the telescopes. So that should be pretty exciting. Once it gets dark enough. All right. So yeah, some of the protoplanets, you know, they became the planets that we have today. But there's still actually some good examples, some good representations of these protoplanets, you know, that I'm talking about that live in our solar system today. And these two objects, Vesta and Ceres, they actually live in the asteroid belt between Mars and Jupiter. And these are the two largest objects. Vesta is actually an asteroid, and Ceres is a different type of object. Anybody know what type of object Ceres is? Very close, very, very, very close. A planet, what kind of planet? A
Small.
dwarf planet. So that's a new categorization, you know, that we've introduced, you know, in science, since after 2000.
Is that what Pluto is too?
Yes,
Oh.
another good representation of what these protoplanets are actually, you know, these dwarf planets, and Pluto is another one. So I like to pause here, you know, because this is actually another good example of science, you know, improving and changing. You know, as our knowledge increases, things get reclassified, all right? All right, so everyone knows that Pluto was, you know, reclassified to be a dwarf planet. That's why it's not on the posters anymore. But there's good reason for that. And that's because in the early 2000s, we started to discover all kinds of more stuff out on the edge of our solar system, out, you know, in the Kuiper Belt where Pluto lives. We think that there could be, you know, 100 or more dwarf planets out there. So far, we've discovered 5 more dwarf planets. But, well, actually, no, Pluto, and then Ceres, and then 3 more dwarf planets out in the Kuiper Belt. But we think that there could be 100 or so. We don't know. It's so big out there. So because of that, you know, can you imagine having, you know, eventually having 100 planets, you know, on a planet poster? That's just too many to remember, right? We can't handle that. But so there's 2 good rules, you know, there's 2 guidelines on what is an official planet, and those are you have to be big enough to make yourself round. All right, so and Pluto obviously did that, so you know, good job, Pluto. But you also have to clear your orbit of debris, okay? But guess what? Pluto lives in an asteroid belt. It did not clear its orbit of debris. All right, and the same thing with, I'm gonna go back a slide, Paul. The same thing with, you know, Ceres. All right, Ceres lives in an asteroid belt, the inner asteroid belt. All right, so it has not cleared its orbit of debris either. And to continue this kind of off to the side note here, this tangent, Ceres was discovered in 1800, I think 1801. All right, and I bet a lot of us have not heard of Ceres before. It's actually pretty cool. I encourage everyone to do some reading on it. When it was discovered, it was actually a planet. We categorized it as one of the planets. But then we discovered that it lived in an asteroid belt, and then it became a rock or an asteroid, just an asteroid. For almost 100 years, or yeah, over 100 years, it was an asteroid. And then as Pluto was being reclassified as a dwarf planet, so was Ceres. So Ceres went from planet to asteroid and then to dwarf planets. And that is, I think, a good example of science just showing the progress of knowledge. Yeah.
So is the difference between a dwarf planet and a prototype planet, the stage in which the solar system is in? Like, are you assuming that
Right,
dwarf
so,
planets aren't getting any more accumulation?
right, yeah, so we don't have like that swirling disk of, we don't have enough stuff to make new planets
Yeah,
anymore,
okay.
right? So, the term protoplanet is specifically referring to these first planets that were emerging in the solar system. All right, well, yeah, so back to our protoplanet story, go past the Pluto. I want to talk about two protoplanets, one of them being Earth, and then the other one being a theoretical protoplanet that was forming in our inner solar system. And we've actually named this theoretical protoplanet Theia. All right, so this is actually a size representation between Earth and there's actually Mars. This is how big Mars is compared to Earth if you put them side by side. When I learned this, I was actually surprised. I was like, wow, Earth is so much bigger than Mars. But Theia, we think Theia was about the size of Mars. All right. And Theia and Earth, again, they lived in the early solar system. They lived in the inner solar system. And they lived on a strikingly the same orbit, all right? And they were just destined to meet in a big way. And eventually Theia caught up to Earth and just smashed into it. And they just collided big time. When I'm talking, this is when planets collide for real. And so Theia smashed into Earth, ejected material out into space. Theia would have been vaporized and Earth would have turned into a big kind of loopy glob mess, but it would have retained its mass, and therefore it would have retained its gravity, and it would have pulled all of that ejected material back into its orbit, and then pulled it in, and then eventually it would have had its own kind of accretion disk. Much like the early accretion disk that was swirling around our sun that all the protoplanets formed from, we think the same thing would have happened around Earth. So here's a nice diagram of Theia coming in, smashing into Earth, ejecting material, and then, over time coalescing, into our moon. All right, so this was before the dinosaurs. This was way long time ago. This was just a little bit after, the formation of the solar system, essentially. So this is the most current scientific hypothesis, and it's called the giant impact hypothesis. I know it gets right to the point, right? It's very descriptive, and that's good. That's so we understand what's happening. But this theory actually, explains a lot of those things that the other ones don't. So I was saying, the moon's core is very small compared to its overall size. So this explains it so when Theia smashed in, all of the heavy, core material of Theia would have fallen to Earth, all right, because of gravity, and all the lighter stuff would have, ejected out, into space. And then as it coalesced, the moon would have formed with more of that lighter material. It also explains the orbits, of our moon. Our moon has a very high, it's going really fast. And we're actually losing the moon. I don't know if you guys have heard that, but the moon's getting farther away from us because it's speeding up. And it's getting about almost an inch farther away every year. And because of that, Earth's day is actually slowing down. Our days are getting just slightly longer. And the math and the computer simulations that we've been able to come up with to simulate this, they actually show this fairly easily. All right, and that's something that we couldn't do until the 80s. When computers really started to take hold and have these simulations that we could utilize. And whereas like the capture theory, we could just work through it with math and be like, oh yeah, this is impossible. Well, the math actually shows us that this is possible. And it's possible so much that it didn't even have to be one giant object. It could actually be a few smaller Theas, that make about the same size as Mars, could have done the same thing. So these computer simulations are showing that the orbit of the moon, is right now that we have is possible by this impact. It also is a good explanation on why the Earth has a tilt. We have a pretty substantial tilt, and we think at one point we didn't, but we think a giant impact could have caused that as well. One other thing that I think is fascinating about the moon's orbit is that, so if you imagine our solar system, all right, and the sun, has an equator that goes out, it's like the equatorial plane of our solar system. Where pretty much all of the planets, it's called the ecliptic. That's where all the planets kind of roll around on. That's where they all kind of orbit around on. Well, the moon's orbit is actually closer to that than the Earth's, equatorial plane, which is really slanted because of our tilts. So I think that's fascinating, that the moon is more aligned, with the solar system than Earth's own, equatorial plane, which has a tilt. All right. So while this was taking place, Earth, the planets colliding and then recoalescing, and Earth, after this impact would have been a big molten ball, but it would have started to cool off eventually, and same with the moon starting to coalesce, and once it became the moon, it would have started to cool off and form an outer shell. Other things were taking place in our solar system. All right, so it was obviously a very chaotic place, right? Planets were colliding. Well, all the other planets, were still trying to find their place, their balance. And right now, we have a very balanced solar system. It's called all the planets have a very balanced orbital resonance. So they're not really changing each other's orbits. Everything is very balanced. But back then, things were still trying to find their space. And Jupiter was getting bigger, and it was actually getting farther away from the sun, and it was pushing on Saturn, and Saturn pushed on Neptune, and Neptune pushed on Uranus. We actually think that Neptune and Uranus could have swapped positions in the solar system at one point as things were finding their spot. And Neptune, we think, could have been pushed all the way out into the Kuiper Belt, out where Pluto is. And as it did, it would have just plowed through all of this, these rocks and this asteroid field. This, by the way, is an exaggeration. Our asteroid belts and fields, they do not have this many rocks. This is very much like Star Wars, and it's very much just to satisfy our imaginations. The inner asteroid belt and the Kuiper belt, I mean, they're just mostly empty. All right, but this contributes to good story. So imagine Neptune plowing through this asteroid field and just flinging all of this stuff into the inner solar system. Okay. Here's another very nice diagram of Neptune doing that exact thing, grabbing an asteroid or a comet and throwing into the solar system. Jupiter and Saturn and the other gas giants, they would have just kind of acted as slingshots and captured this stuff and spun it around even more and turned the inner solar system into a giant grinder, essentially. Just filled the inner solar system with debris. And all of the inner planets, all of the moons around the gas giants just would have been pulverized, just bombarded by all of this Kuiper Belt material. We actually call this time, this period in our solar system, the heavy bombardment, when just everything just got pulverized and covered in craters, essentially. And we see evidence of this all through our solar system on the moons. This is the moon of Saturn. This is Dione. We can see it's just covered in craters. It looks a lot like our moon, doesn't it? Here's another crater with a mountain right in the middle of it. But here's another moon of Saturn. Wait a minute, that's no moon, right? That's a space station. I don't know if anybody has ever seen Star Wars, but the resemblance is uncanny. All right, that is definitely the Death Star. I don't know if you guys think the same thing, but if George Lucas did not get his inspiration from this exact object, I don't know where it came from. But this is actually a moon of Saturn. This is Mimas, and you can see it's just a giant crater right there with another big mountain, and then just covered in craters. And the same thing with our moon, it's covered in craters from the heavy bombardment. All right, so if the whole inner solar system got filled, and just covered in craters, what about Earth? Do we see evidence of the heavy bombardment on Earth? Well, we don't really, and does anybody know why? Anybody have an idea of why we don't see?
They're in the ocean?
Well, the ocean, that's a good train of thought there.
The crust keeps
It,
renewing.
yes, erosion. The Earth has erosion, all right? We have an atmosphere, we have wind, we have rain, right? We have tectonic activity, volcanoes, earthquakes, and then just life on our planet. So the outer crust of Earth, is relatively, the very outer layers is relatively young compared to the solar system because it's constantly changing. Whereas everything on the moon is extremely, extremely ancient. Nothing has changed on the moon except us just recently. This is not ancient. This is actually fairly new, but guess what? Someday it's going to be ancient because there's no erosion on the moon. Hardly at all. There's solar erosion, which is just, the sun beating down on the rocks. I don't know if you can imagine, just a sun beating on a rock on Earth. Even for 1 million years, it's not going to do very much, right? The moon is getting hit with micrometeorites, every now and then. But this footprint is going to last for millions of years potentially, because there's no atmosphere, there's no tectonic activity to speak of on the moon. There's just no erosion. So the moon is actually a really good time capsule of our very early solar system, which is cool. We get to see what the solar system was like billions of years ago by just looking at our moon, because nothing has changed on our moon. All right, well, let's talk about, the whole moon, is a product of a giant collision. Let's talk about these lighter and darker areas so far. So the lighter areas are known as the highlands. And they're actually a little bit more of an older region on the moon. These lighter areas are covered in a really fine powdered dust called regolith. And that's where we see most of the, all of the evidence of the heavy bombardment actually is in the highlands, those lighter areas. And there's just this very mountainous, there's a lot of rocks, there's a lot of elevation, change in the highlands, makes sense, right? When we take a closer look, we can see it's crater and inside of crater, all over the highlands. Here's a picture from one of the Apollo missions. This is actually Apollo 17, the last mission that we went to the moon. You can see, the astronaut just got done doing some donuts here. He's gonna go over and check out some rocks. Here's some really big rocks over here, and on the horizon, we see this very mountainous landscape right there on the horizon, because that's because the Apollo 17, they actually landed right next. They landed in the Maria, which is the darker area, but they landed right next to the highlands. So that's what this is back in the background. One crater, I like to touch on real quick. It's actually located in the highlands. It's called Tycho, and it is kind of at the bottom of the moon there. This crater is actually about 50 miles across, 50 or 60 miles across. You can see the ejecta rays that just span out for hundreds and hundreds of miles all across the surface of the moon there. And just the impact was massive, right? From this meteorite impact that formed Tycho. We look at it from the top down view. We can see that around the edge, this is like the Grand Canyon here. There's these cliffs that go into the crater. And then right in the middle, there is another mountain, all right? So we've seen that a couple of times. And when you come out and look through the telescopes, when we do look at the moon, you'll actually see, some of these little mountain peaks in the middle of craters. And you'd think if a big object, big meteorite came in and just smashed into the surface of the moon, just leave a big hole, right? Why do we get these mountains in the middle of these craters? Well, it's the same principle as when you drop something in water, right? You get that initial splash out with those ripples, that form the crater, but then there is a recoil, right? You get that reaction that comes, that bloop that comes back up. If it's enough energy, when the moon, when these craters were made with these mountain peaks, the surface would have liquefied from the energy, and then that recoil would have gone up, and then this bloop right here would have settled back down as a mountain. And this is the mountain in the middle of Tycho. This mountain is a mile high from the crater, from the bottom of the crater there, pretty much. So there's a big recoil, isn't it? Big bloop, little drop coming back down. And we see that when we look through the telescopes, we can see these little mountain peaks in the middle of lots of craters. Not all of them, but some of them have these little mountain peaks right in the middle of them. All right, well, that's the highlands. Let's talk about the dark areas. That's again called the Maria. And it's called the Maria because ancient humans, and ancient astronomers, we used to think that these darker areas, they actually could have been oceans, of water, up on the moon. And if you translate Maria, it literally translates as seas, the seas on the moon. But there was never oceans of water. There's never oceans of water on the moon. These seas were actually oceans of lava at one point. All right, so just imagine, going out and looking at the moon now. Imagine if those were just like glowing red seas of lava at one point. That'd be pretty cool, huh? So where did these oceans of lava come from? Well, again, on the same, you'll notice a theme here is big impacts. All right, you can see some of the Maria, they're very circular, especially this one. I mean, it looks like it's a giant impact crater. All right, and these they're so big, something came in, smashed into the moon, and fractured the crust. So we think at this point in the moon's history, it still had a molten core. Nowadays, the moon it's completely cooled off, essentially. As far as we know, it's like just a big cold rock. But back then, it just had a core, an outer crust, but the core was still molten. There was still lava. But these impacts, they were so big that formed the Maria. They fractured the crust, and then this magma, this molten lava, flowed up through those cracks. It filled up those impact basins and spilled out over the lunar landscape. And we can see when we look, here's a picture from the Apollo 11 mission here. We can see there's a nice view of the Maria. They're very, very flat, right? Just imagine this liquid, flowing up and then leveling out, and spilling out over the lunar landscape. So it makes sense that, we wanted to land here, right? Instead of in the highlands. It's much flatter, not as many mountains, not as many rocks. You know, way better choice to land in the Maria. This is the Sea of Tranquility, by the way. So the Maria, all of this stuff is basically basalt. And it's the same stuff on Earth, essentially. Same basalt that comes out of volcanoes. You know, when you think of lava flowing out of, you know, the volcanoes in Hawaii and like volcanoes in Iceland, and the lava flows around here, you know, they're basalt, and the same, almost the same exact stuff, you know, on the moon. Because, you know, the moon is essentially, you know, part of Earth from that impact. They share, you know, they're almost, you know, identical as far as, you know, what minerals are on the moon, you know, compared to Earth there. So it's the same basalt stuff. Paul was telling me that it's interesting, you know, the basalt here around Central Oregon, over in the lava fields, the lunar missions, we actually trained astronauts out on the lava fields over here because they thought that it might be similar, you know, to the lava, you know, up on the moon. All right, so one last thing about I know I have a couple more things. So the Maria, we think, happened after the heavy bombardment, and we see evidence of that because of these right here. These are known as ghost craters. All right, these craters that are just partially filled in, you know, they're just a little bit covered over. So the heavy bombardment happened first, and then something after the heavy bombardment, these really big objects came in, smashed into the moon, and then made these seas of lava that spilled out over, you know, all the evidence of the heavy bombardment. But we see evidence of some of these poking through, you know, out of the Maria. Again, these are called ghost craters. So that's why we think, you know, the Maria happened after the heavy bombardment. Well, if it happened after, you know, where did these big objects come from that form these giant seas of lava? Well, this is still, you know, very debatable. We're not quite sure. There's a few, you know, hypotheses, few theories out there. You know, some people think that it could have just been kind of like a late heavy bombardment with these much larger objects that came in. But I like the theory, the hypothesis of they could have come from the moon's orbit, you know, just right at the Earth. All right, if we go back to this slide, you know, Theia coming in, smashing into Earth and forming this debris field. We get the moon coalescing right here, but we also get a lot of other smaller things coalescing together as well at the same time. So these actually, the moon or the Earth could have had more than one moon at one point, potentially, right? We know we have our one moon right now, but we could have had one big moon and then a bunch of little mini moons as well, orbiting around our planet at one point. And eventually, because of the same principles as those rocks smashing together, forming bigger rocks that we talked about at the beginning, those little mini moons could have coalesced, you know, into, you know, the moon that we have today. All right, well, now you know a little bit more about the moon, right? You know about the Highlands, the story of Neptune plowing through the Kuiper Belt, filling the inner solar system with the debris and forming the heavy bombardment that caused all of these craters. You know about the story of the Maria, giant seas of lava that were formed from even bigger impacts. And then the moon itself is the product of one massive impact of planets colliding. All right, and all of this history, all of these different terrain features, when you go and look at the moon now, you know, think of these stories, you know, and try not to take it for granted. It's just like a big ball up in the sky that we kind of forget about, right? Try to think of it, you know, as a whole nother world, you know, with all of its own history. Tonight, we're actually not going to see the moon, which is a little unfortunate, but I can tell you, come back and look at the moon through the telescopes because it's actually one of my favorite things to look at. you know, when we are looking at the moon. Tonight, we're at about this phase. It's actually rising around 1:30 this morning. I won't be up that late, but you will be able to see it over in the morning over the mountains. You know, in the day, I think it sets around 9:30 tomorrow morning. So if you look over the mountains, if it's clear, you'll be able to see it in the west. My favorite time to look at the moon through the telescope, if you guys want to come and look, is actually when it's crescent like this. Okay, and that's because we have this shadow line right here. My least favorite time to look at the moon is when it's full, like this. So it's all about that shadow line. It makes the moon really cool. And that shadow line is actually sunrise on the moon, you know, on this side. On this side, it's sunset. But when it's when it's sunrise, that shadow, imagine here on Earth, you know, at sunrise or sunset, you get those really long shadows. Well, the same thing happens on the moon. And those really long shadows are what really accentuate the crater rims, you know, any ridges that we see on the moon, lava ridges, or even those little mountain peaks, you know, in the middle of the craters are just really brought to life by those big shadows. So this is actually my favorite time, you know, to look at the moon. All right. Well, I think that concludes the talk for this evening. Yeah, we're about 5:30 right now. I want to thank everybody for coming tonight. And if you have any questions, you know, we can stay and chat more about the moon. All right. Well, thank you very much. Yeah.
So if something hit the earth, the collision theory, and why isn't there a scar? Or some physical representation?
So we think that the energy would have been so much that, so the Theia coming in would have been pretty much vaporized, you know, disintegrated and, you know, just completely torn apart. And then the Earth would have actually turned into a big ball of magma, essentially. Just so it would have been whatever Earth was would have been completely renewed at that point. So none of the outer crust would have stayed intact, essentially. So just, yeah, like a big loopy, just imagine a big loopy mess of debris or lava.
So it wasn't a gaseous, non-solid that collided.
No, it was a terrestrial rocky, you know, planet, much like the inner planets that we have now, you know, like Venus and Mercury and Mars and Earth. They're all, you know, terrestrial rocky planets. We think Theia would have been the same thing, a rocky planet like that.
Yeah, thanks.
Yeah.
So like Saturn and Jupiter with their many moons, they have many moons because they're bigger, so they have a bigger mass, so that all.
Yeah, so and their moons, you know, we think, you know, some of those theories that I was talking about with you know, that didn't make sense with our moon. We think that some of those theories actually make sense with the gas giant moons. You know, a lot of those objects, those moons, they could have been captured because of the gravity of those larger bodies. And, you know, some of those, they could have formed, you know, kind of at the same time and just kind of formed with those gas giants as well. So like the co-accretion and the capture theory could potentially explain some of the gas giant moons. So, but it doesn't really explain everything about our moon. Our moon's a little different.
Tim?
Yeah.
So after the collision, and you showed the clip of the Earth tilting, but yet the debris field was on a different plane. Is there a theory about why that happened?
Yeah, so that's one of the supporting examples of why we think that it was a collision, you know, from another planetary body like that. So it would have shared the same sort of orbital plane, you know, as Earth. All right. So the moon's orbit, the plane of, the moon's orbit is very similar to, the plane of our solar system that, all of the other planets share. So so even after the collision, that's, that inertia, retention of momentum would have kept that same sort of motion, and then it would have, that, the reason, the orbit would have been similar.
Got
like
it.
that. The Earth's, it still has that orbit as well, but it's tilted, the axis is just tilted.
How did they determine that we're tilted?
How do we know that we're tilted?
Yeah.
Things are higher and.
The seasons.
Yeah.
Are a good, way
Okay,
to know
yeah.
that the Earth is tilted,
Okay.
yeah. Yeah. Any other questions? If not, feel free, we have, maybe some more snacks and some sodas back there. And then, I guess we can open up the observatory, right?
Yeah.
And just kind of, check it out and wait for it to get dark. Those of you who want to, stay and look through a telescope, we plan on looking at Mars and Jupiter, here in a little while. It's probably gonna be, a good 45 minutes, I think, until we, get the planets in the telescopes, just because, the day is getting a little bit longer. But yeah, feel free to hang out. All right, thank you, guys.
Oh, I wouldn't.
Thanks.
Learning right away.
Oh, thank you very much.
Gonna stay for the
Gary,
telescope.
yes, you're on.
Well, it's a marvelous night for a moon dance with the stars unfurling and heaven is back to make romance neath the cover of a Taurus sky. With all the leaves on the trees are.
No, it's not on that side of the river.
Yeah, I'm trying to please to the calling of your heartstrings that play soft and low. Get all the night.